everyone. I would like to first thank MMU for hosting this event and to the IEEE Women in Engineering for inviting me to this event. It's been a great and really interesting topic so far. Mine's going to be a bit more technical, but I'll try to link it a bit more to the theme. I'll be talking about the recent advances in electromagnetic sensor development, mainly for power station, aerospace, and generally NDT, non-destructive testing applications. A little about me. I am a lead researcher for some of the selected projects that are there for developing field deployable electromagnetic sensors for power stations, which I will describe later on, electromagnetic defect detection, and also damage detection for aerospace industries. So we'll walk you through some of these selected European projects. Okay, so just like any other problem, we need to know what the problem is. We need to be able to provide methods and therefore solutions. We might be aware that power stations currently are being operated at really high temperature and high pressure. That's mainly to increase the efficiency and reduce the carbon dioxide emission. So any failure of these steel materials will have severe economic and environmental impact. Currently, there are detailed and frequent inspection are being taken place, but they are really costly and they take place on the shutdown periods. So it's really important to measure these microstructural properties of these steels in the power stations through detailed and frequent inspections. So far, no single technique has been proposed to the full monitoring of these microstructural properties during in situ time. So that's what we want to do. So just to provide you with a brief techniques and the materials that we use, we usually design, simulate, fabricate, and test the electromagnetic sensors. We take the output from these sensors, link it to the finite element method responses that we have. Through the spectroscopy measurement, we get the magnetic properties. Through metallurgy and material testing, we get the microstructural properties, which is eventually enough information to tell us whether something is being degraded or not. Something that adds to the importance of this project is that if materials fail, and if power stations shut down because of a failure of a power station steel materials, one power station shut down per day will cost £1 billion. So it's a huge economical impact as well as environmental. So these are the type of electromagnetic sensors that myself and my group have designed. So the small one is for small samples, and the big one is eventually made for the real world samples. So what we have is a hands-on sensor, electromagnetic sensors, that we can take in situ with us, put on samples, steel samples, and that would be able to give us electromagnetic properties like permeability, conductivity, and also material properties, which can eventually tell us whether the material is being degraded or not. Okay, so I'll walk you through the next European project that I was involved in. This was funded by the RCNDE, which is the UK Research Centre for Non-Destructive Evaluation. So this is usually used for defect detection. As you can see, it applies to pipe, undersea, in the soil, trains, or rail lines. Okay, so currently the problem is that the single coils are being used, which are not sensitive enough to detect these defects. And they're really sensitive to lift-off and to edge effects. And they could, a lot of the times, reject the screening methods. And so in order to do that, we need to propose something called eddy current arrays. So this is a coil, single coil. As you can see, it doesn't cover the surface. And in these cases, the probe must be kept normal to the material, which is a bit difficult with complex geometries. So what we need is an array of them that could cover the whole surface. Okay? So in order to do that, which has a huge advantage of being adaptable and comfortable and on multiple geometry, for multiple geometry inspection, we started with designing finite element methods. This is a single coil mainly because of the computational load, but this can be made into an array. So as you can see that there is a huge defect there that is easily being picked up. And this is a video of the simulation. So what we'll be moving is the defects. So we've got the coils, and what we have moving is the defect. So by changing the defect position, the eddy currents which are surrounded the coil, they change. And that can tell us that the defect is easily detectable, no matter where it is in the material. Okay? I'll let that run through. Okay. So in order to do that, we designed something called eddy current arrays, which doesn't have one coil, but it has many coils, multiple coils, which are semi-flexible, and they can cover up to 20 millimeters, which is 2 centimeters coverage, so it's basically this, and it's got a transmit receive. And we measured the titanium material with 4 defects, 8 millimeter and 10 millimeter. So imagine this is going to be on a huge material. This was just a lab test. And it easily picked up the differences between the 2 defects, which is good. Okay, so the next one, the next European project that I was involved in was supported by the University of Manchester Aerospace Research Institute. It concentrated on damage detection. So a coupled spiral inductor sensor was developed, which, as you can see, is half of a pound size. For that, we improved it. We added a ferrite layer to the bottom, which improved the sensitivity. We then realized that, yes, okay, this is great. It can detect a lot of defects, but let's do something new. We got a yoke, ferrite yoke, and we encircled it with a coil. We realized, oh God, that is great because it can detect a lot more sensitive defects and a lot more smaller defects. So this is just a result of how different defects and voids can be detected by the 3 sensors. There's some publication ongoing on that, so if you want more details, then I can pass that through. Because this was a really interesting and successful project, there was some interest from the wind turbines industry, and it's already been tested on some of the wind turbine blades, which is quite interesting because it shows the importance of this research and how applicable it can be to different industries. My other involvements, as well as doing some research and teaching at the University of Manchester, I'm also a treasurer of the IEEE UK and Ireland section. I'm a committee member of the IEEE UK and Ireland Women in Engineering, and a committee member of University of Manchester IEEE student branch. So the projects that I showed you, going back to the theme of the whole event, shows that a female engineer can get involved in a huge European project, not only get involved, but be successful and make a difference to a huge industrial projects that can eventually make a difference in our lives. And that's all I have to say. Thank you very much for your attention.